I think that we should move to our special talk. The last speaker of the day from Vienna. Is a very honor to have Professor Wladyslaw Szymanski. Professor Szymanski is very acquainted to Thailand, and actually he should have been in Thailand during this time of the year, but could not come because of COVID-19. Hopefully you can come soon. He is affiliated with the Aerosol Physics and Environmental Physics Group, Faculty of Physics, University of Vienna. And Professor Szymanski has the doctoral in experimental physics from University of Vienna, and he has been the visiting professor at Kasetsart University in Bangkok since 2012 up to now. And his research interests in environmental science aspect related to aerosol like air quality, PM sampling, and characterization of atmospheric constituents, aerosol physics and applied particle technology, biotechnological application related to nanoparticles and bioaerosol. And he has over 100 contributions to international journals, books, and periodicals, and 5 patents. And his talk today is a very interesting and very a big issue in Thailand that's received a lot of attention. It's a low cost and optical sensor and the applicability for measurement of ambient PMX. Because now in Thailand, we are discussing a lot about using the low cost optical sensor for measuring the PM, especially PM 2.5, so that we can have a lot of sensor, a lot of the data for Thailand for the monitoring purpose. And his lecture today will be very useful. May I ask one question? Actually, permission from Professor Szymanski, that can we have your talk recorded and distributed to the public in Thailand in case somebody are interested to listen to your lecture?
Yes, I have no problem with that. Please do.
Okay, thank you. So that now is your time to give a presentation. Thank you so much.
Thank you. Okay, can you see my presentation now?
Yes, I see your presentation. Yeah. Yes, perfect. Yeah.
Lovely. And so how about the reception? Because I'm talking on an internet connection from my home, not from the university. Can you hear me well?
Yes, we can hear you very well, very clear. And your background is also beautiful.
Yeah, beautiful. Yeah.
Thank you. You are very kind. Well, Professor Pirapong, thank you very much for your kind words and for having me taking part in this very interesting workshop showing huge number of database, which still has to be, I think, digested, but I learned already quite a few things listening to the talks. Also, thank you to Professor Ferrucci to asking also me to join you. So I will talk about low-cost optical sensors because I think this is an important issue, as Professor Pirapong mentioned. First of all, I would, however, like to focus in a few slides on an issue which we all know, but I have the feeling that sometimes we are losing sort of a bit sensitivity what we do. So let's try to get the feel of PMX. We are talking always on PM 0.1, PM 1, PM 2.5, etc. So I put here a few slides that every one of us who measures these values is aware of the complexity of the measurement. So when you look at the slide here, you see I put here some from nanoparticles to coarse particles some spheres. And this big sphere relates to PM10 size. This would be PM2.5, PM1, and these are ultrafine particles or nanoparticles. When you look at that, you can ask yourself, well, you know, we try to assess air quality based on the mass of particles. And when we do that, let's focus on the fact that one aerosol particle with 2.5 micrometer, PM2.5, has the same health hazard. It means also the same mass, because we measure mass, as 1 million of nanoparticles with 25 nanometers. Now we are measuring nanoparticles as we did see during this workshop. So it is a very, very hard job, really, to obtain the mass of nanoparticles. We should always keep that in mind. Moreover, when you look at the particle size range here, as the particle is getting smaller and smaller, the number of particles increases. But if you measure mass, you have to keep in mind that very few big particles have a lot of mass, and nanoparticles have only a very little mass. Now, when we are talking about air quality or air pollution, we are looking over a city in some area, whether this is Kanazawa or Hatyai or Kuala Lumpur, and we measure at one spot, and we want to know something about particulate matter there. So we ask for a question, how big these particles are, how many, and how do I get the data? Because we can do some monitoring in real time, and this is what I will be focusing in my talk today. But of course, what is very important, what we also do and what was reported in this workshop is particle sampling for chemical analysis. And we did hear that some people sample over 1 day, some people sample over 2 hours. So the question which we ask, what is the appropriate method and what is the time scale to represent the factual air quality? Because we're not interested in the numbers only, we're interested in what is happening in this spot here to give us some idea about the quality of air in the area. So do we need to measure quickly, within 1 minute, or do we have time for 1 day or even longer, like 1 year, which is important for some statistical analysis? Now, when we look at the same slide which we did see before, I will indicate here a few methods. If we look at particles size range from nanoparticles to coarse particles, the mechanical methods, whether they are reference methods or filter sampling or impactor sampling, are not in real time, however, very important for chemical analysis. The electrical methods, we are not talking about that, are very interesting for nanoparticles, but I will be focusing today on the optical methods. And the reason I'm looking at that, because this optical type of measurement, also electrical methods, which we skip today, are real-time. And the question is, how important is real-time measurement? I will show you here a slide which shows you the actual pollutant levels. This is this line here. And then if we average over 1 hour, the same measurement, you see the dotted line. If we average this measurement over 8 hours, we are getting the solid blue line. So what happens when we do the averaging, we are losing the information about some maybe very important pollution episodes. It doesn't mean that we should not collect and over a long time data because we need it for apportionment and chemical analysis. But it is very striking that if you don't measure quickly, then in real time that you are losing maybe some vital information. Now, so optical real-time measurement is something which we would like to do because it's fast, and so I show you it's not very expensive. Now, what is the crux with the optical measurement? Well, We like to get from optical measurement the indication of size, fraction, PM 0.1, PM1, PM 2.5, and amount. Now, usually the amount is defined with mass concentration. So it is weight in a volume. Well, but what we measure number. And this is the critical issue when using low-cost sensors. So we can have with optical measurement a real-time direct number concentration measurement. What we are getting frequently from low-cost sensors is real-time indirect mass concentration determination, which is the primary optical data mixed with some environmental data and a lot of software. And I'll be focusing on that in a minute. Now, let's look at the low-cost PM air quality sensors. What are the expectations? We want to have, and we have, small price, small size, and a perfect air quality data. Is it important? Yes. It is possible. Let us see together. So I will discuss in a few following slides the principle of operation and related problem of the operation. I will indicate some issues regarding the laboratory and field studies with low quality optical low-cost sensors. They're also low quality, by the way, frequently. Then some measuring experience from some recent data which I found. I will talk about the need for the harmonized terminology for low-cost sensors so we can have some comparison, and I will then summarize my talk. So I hope that is something which is of interest to you as well, and I invite you to follow my slides. Now, nowadays expectation, when you go to Google and you hit low-cost sensors, in 0.46 seconds, I got over 7 million hits. So the expectation today, we want high-quality data at a very low cost. Look at the costs of the sensors, some 200 to 1,000 baht, and they all give you some data. Now, what is the most common principle for these low-cost sensors? Well, there are two types of measurements which are used. In some low-cost sensors, we have a light source which is focused on a spot in space, and when some particle passes through the beam of light, it scatters some light to a photodetector, and then we measure a pulse. And then those pulses can be also counted, so we know how many. The other sort of measurement, which we have is the situation where we have a lot of particles passing through the beam of light, and either the detector can be looking into the laser, which is rather rare. We would have then a weakening of the signal because of the presence of the particles, or when we have the detector off the line from the laser, we would have some increased signal coming from the presence of the particles. But this is all information which you are getting from any real-time optical sensor. Now, so the principle, as I mentioned, is simple. We have a source of light, particulate matter, and a detector. Now, we have to keep in mind that this signal measured by the detector depends not on the particle size and amount of particles, but also on the particle material, which is reflected by the so-called complex refractive index. So there are two numbers which we don't know. And then there's also particle density, because if you measure a number of particles and you want to have mass, you need some information about the particle density, which can vary for particles which are present in atmosphere from 1 to 8. So we have factor of 8 unknown already here. So having that in mind, where is the actual problem with the low-cost particle matter sensors? Well, the problem is the conversion of the measured optical particle size to size resolved mass, like PM2.5 data. And this simple equation shows you, for the simplest possible case, we have only particles of one size. So the optical sensor measures particle size. We don't know what is the accuracy of the measurement. What we also measure is the number concentration. How many particles were measured by the sensor per cubic meter of air? And then from these two numbers, we try to infer mass concentrations in microgram per cubic meter, but we don't know the particle density. So even if we would say that we know average particle density, still, if we don't measure the size very accurately, so if we measure, and if we have an error in size determination of 25%, this can result in a difference for volume or mass concentration of a factor of 2.4, which is 240%. So we have here a formidable problem with the conversion of measured data into type of data we want to have. Now let's look at the moderate cost versus very low cost optical instruments. So you see here the low cost instrument in its simplicity and size, 5 centimeters. This is a moderate, small optical particle spectrometer. It counts particles and does measure the particle size. You see here some size distribution, and you see that the internal life in terms of definition of the system is quite complex. So the main differences between, sorry, my computer does a little bit by itself. So main differences which we have is we have here a well-defined system versus poorly defined system. We have in the, say, research grade instrument, a controlled operation, calibration record, accuracy information, repeatability, bigger size and bigger price. So we have to keep in mind that once we reach for low cost optical measurement, we are losing the situation where we have a well-defined system. Now, what are the basic types of the low-cost sensors? There are two. The upper row here shows you the so-called nephelometric measurement. We have here a light source and a photo detection unit. Particles are moving through a volume, and when they are moving through the beam of light, they scattered some information, and this is the only signal which we have. It is a signal from many particles at the same time. The other possibility which we have is the single particle measurement. Let's look at this one here, like a Honeywell. There are few selected types. I'm not trying to convince you that some of these types are better than the other. So here, one by one particles move through the beam of light, and they can be counted and then by some software converted. Inside the low-cost sensor, you see that the situation is very simple. There is a light source, there is some photo detecting system, and particles are moving somehow through this area here. And that's it. What we have here, it's a resistant heating element. It is not unimportant because, as I will show you a little later, the stability of the light, which is illuminating particles, depends on the ambient temperature. So when the ambient temperature go up, the intensity of various either light emitting diodes or semiconductor lasers, they're all very cheap nowadays, the stability changes. And usually when the temperature goes up, the illumination power drops. When you have less light to be scattered on a particle, your signal is lower. That means your recalculated mass concentration is also lower. So this is just a summary what we have kind of problems which we use low-cost sensors because these issues are almost never addressed, which is the accuracy. What is the difference between the measured and the actual particle size? the sensitivity. What is the smallest size I can measure with the local sensor? Is it 0.5 micron? Is it 0.1 micron? If I measure a number of particles, what is the counting efficiency? Do I measure every single particles? And how about the repeatability of data and flow rate? If the flow rate is unstable, the number and mass concentration is also varying. If you go to ensemble measurement, which for low-cost sensors, and I will try to prove it later, I like better than single particle measurement, we have the same problem. Oops, I lost my presentation. Yes, we have the same problem with accuracy, sensitivity, and precision. So now look at the laboratory calibration of low-cost sensors. If we calibrate this local sensor in the laboratory, it's actually a lot of work, but it's a straightforward problem. We need calibration particles. We need to know the material of the particles. We can control the charging state of the particles. Are they neutralized, no electrical charge of particles, or are they electrically charged? Why I'm addressing this? Because if particles are electrically charged, the low-cost sensors, usually the casting is made of plastic. And if this is made of plastic, you can have a static charge islands on the plastic surface. And electrostatic force is by far the largest force when it comes to removal of particles. So small charged particles will be removed within the sensor and not measured. And then we need controlled environmental conditions, which in laboratory is easy. If we go to field calibration, which happens to many of us, if you take your other instruments and go into the field, how do our measurements relate to the measurement by the low-cost sensor? So we need to obtain some information either versus some Fedor reference method or gravimetrically, having a simultaneous measurement of the particle mass on the filter, which we do all the time. We need to select some reference instrument. It ideally would be to recalibrate the low-cost sensors with ambient particles if possible. And then we need to look at the placement of the low-cost sensors versus the other reference sensor, which supposedly should be better because it's a research-grade instrument. And this was addressed today already in the discussion, where to place our measuring instrument. There are wind conditions, eddies in the area. Are they enhancing the measured concentration? Are they lowering it? And we always need to continuously monitor temperature and relative humidity when measuring with low-cost sensors, because the output depends on these two values, as I will show you in a minute. Now, this slide I adapted from a publication by Kang Ho-an from Korea. I call this high-cost calibration setup for low-cost sensors. He made a very, very careful setup showing what should be done with low-cost sensors to trust the data a bit. So you have a particle source, you have here test duct, you put here low-cost sensors, you control ambient conditions, and you have here a solid reference instrument, whether these are certified photometers, very well calibrated OPCs, or Fedor reference methods. What calibration particles we can use? We can use some atomizers. We can use some atomizers for polydispersed particles, for liquid or solid particles. We can use some dust dispensers for polydispersed particles, which my computer does something I don't like, which we call Arizona road dust. This is the figure in the middle. And then we have also a source of urban particles, or we can use monodispersed particles, which can be very well defined, but this is more difficult and more expensive procedure. Now, this is something which we all know, but I would like to stress again that even perfectly working measuring instruments, they may produce not perfectly matching results, especially because different instruments measure different particle properties. Like optical instruments measure optical particle properties, And we are only in a very good situation where the particles are spherical. The optical measurement then gives us actually something which refers to the actual particle size. If the particle is longitudinal, optical real-time instruments give us only a scattered light, and we try to infer from the scattered light the particle size. Now, having all that, we usually look at some coefficient of determination between various instruments. So you see here the reference values, observed responses, and we are very happy when our coefficient of determination is close to 1. Many times, as we have seen also today, it can be way lower than 1. Now, in the following slide, I don't want you to see the details. I would like to show you from two publications, from 2017 and 2019, various, on the left-hand side of the box, you see various types of low-cost optical particle sensors. And here on the x-axis, you have the range of reported R². And you see, depending on the in-field calibration, you can have an agreement of 0. So there's no correlation whatsoever. And yet we take some data, many people take some data from such instruments and try to explain the world. So this is a formidable problem which we all face. On the right-hand side, you have different instruments, different correlation, and yet you see also the spread. If we are lucky, the R² is 0.5 or 0.7, and then we're already in an excellent shape. For field studies, again, the variation is very broad. So this is just to show you the extent of the problem. Now let's look at some actual data. The upper picture shows you a measurement of low-cost sensors versus GRIM and TSI instruments. So this is what I would call the research-grade instruments. And you see, as long as the relative humidity is low, this is the concentration indicated in this case by a TSI, agrees with the GRIM very well. And that moment where the humidity goes up, this is the data from various low-cost instruments. So you see, we have here a situation, where the concentration indicated can be 10 times as the actual concentration. And similar situations here are published 2018 by Crilly et al. In atmospheric measurement technology. You have here 14 various optical particle counters, and this bottom dark line here is measurement by research grade instrument, and everything else is PM2.5 measurement by low-cost sensors. Now, can we do further analysis? Well, it's a time response. How quickly a low-cost sensors measures and gives you the data regarding to the situation which happens in actual life. Well, you can see that the time response is not really so bad, except that some low-cost sensors show you after some minutes way lower mass concentrations for the situation shown in the paper by Wang et al. From 2015 and by Li from 2019. So without going into much detail here, we see the problem. And the key point is that people using low-cost sensor ignore most of the time these issues. Now, can we use low-cost sensors at all? Yes, they can be used, but we must know the ambient conditions, which is relative humidity and temperature. And there are various papers now which show for various low-cost sensors, the correction scheme. Like you have here PM2.5 corrected, PM2.5 indicated, and some relationship to ambient conditions. And then the R² improves. Here you see the same. This is measurement here in Glasgow in Scotland on the right-hand side with so-called footboot instrument. also you see the data can be corrected regarding the ambient conditions. Now, more data which shows you further issues. There are various fits which can be used to represent the data. And why I'm saying that, now I'll be stressing this at the end, that all these local sensors use a lot of software to present the data. And we don't know exactly what kind of fitting is used there. It can be linear, it can be exponential, whatever is better. You see that for one fit, we have R 0.8, for the other 0.92. So both would be probably good enough for measurement of ambient situations. And more of that, by the way, I found here in the publication by Kelly et al. From 2017 that what frequently happens to us, a typographical error, January 16, January 26, January should be not January, but should be February 5th here. Happens in peer review that even the reviewers miss the things as well. So having all those issues, why should we use at all real local sensors? Well, because they are actually promising supplement, but only supplement to current monitoring methods. They may enhance, if we know roughly how they work, the resolution and pollution mapping, because they are low cost, so we can have many of them in various spots. Many times we can connect with local sensors over the internet in the meantime. The local sensors can help to assess personal exposure estimation, but I stress here, can help estimation. Many people take for absolute truth what the local sensor shows. That's an error. Now, we can benefit from epidemiological studies because of the exposure estimation. I think that local sensors can be very well applied to transport models, and maybe, if they will be better with the time, prevent pollution events. Now, all that is mirrored by the amount of literature. When you see here, this is from Web of Science from 2019, between 2009 and 2018, the amount of publications regarding use and applicability of local sensors explodes exponentially. So one of the things which we need very, very badly, I think, is to harmonize and to understand what type, or let's call it what level of local sensor in question somebody is using. And the table I summarized and adapted this from Environmental Science and Technology, some recent paper about 1.5 years ago with some of my comments. So I would call the level L0 local sensor is a sensor which provides a raw data measured by the sensor. That means the signal, for example, counts, is proportional to the measurement, to these things what we are measuring. Then the next level, L1, would be a data which is estimated from L0, but there's no further compensation and data is derived, like mass concentration. We are never measuring with local sensor mass concentration. We are measuring an optical signal, and either it will be converted from number concentration, or we are measuring signal from many particles, but then this instrument must be somehow calibrated in terms of a mass. And we don't know this calibration usually. And you can see that it goes further where L2A would be the estimate, the mass concentration with some artifacts for correction, like are we losing particles? Is the inlet sampling all PM2.5 particles? And then we derive mass concentration, but the local sensor measures on board temperature and relative humidity and makes the correction. It goes further, and you can read it yourself. I would like to stress that we have also data, which is in the internet, which I call L4 data. This is the information which tells you what is, for example, the mass concentration, let's say in Bangkok, but this data many times is inferred from network and from some other sources and models. So you are measuring, there's some measured information in spot A and spot B, but in between, you don't have any measurement, but the network provides you estimate based on some model. So we actually have what I call equality based on algorithmic product, because there's no measurement. And yet we get information, well, at this and this spot, we have mass concentration of PM2.5 of 100 microgram per cubic meter. So we have to be aware from what kind of sensor the data comes and what kind of sensor provides what sort of data for the later analysis. So let's put together what I discussed so far. And I hope I'm still on time. Sorry, I didn't look at my watch when I started. Low-cost sensor, the problem is, thank you. I am done in a few minutes and I'll be very happy to discuss. So the problem with low-cost sensor is we are getting a black box. We have no idea if it was calibrated and how it was calibrated, if at all. If we measure with low-cost sensors, we don't know what material are we measuring. We can estimate when we know it's more soot particles, then the density would be somewhere around 1. If we think these are probably particles coming from some mining area, well, the density will be probably between 2 and 3. We also don't know the RI is refractive index, which also influences the measured mass. However, the refractive index is less, well, I would not say it's less important, but influences the nephelometric measurement, where we measure light scattered from many particles at the same time, does not influence as strongly as single particle measurement. And the signals are more stable the more polydispersed the particle material is. Then there's the question of lower detection limit of the sensitivity. Usually low-cost sensors stop measuring between 0.3 and 0.4 micrometers. Well, that means if we measure PM2.5 and we are losing the particles at the low end, you remember from one of my first slides, the small particles have a little mass. So one could think, well, if we have a little mass only, maybe if I cannot count smaller than 0.3, it doesn't matter. But if the other instrument measures only up to 0.4 or 0.5, well, then we may have a problem. From when you think, remember the summary given by Professor Ferrucci in a previous talk, what was for me very interesting to see from the data obtained by the NanoNet, which is a wonderful organization, by the way, he indicated that the fossil fuel burning, likely particles of interest or of importance are larger than 0.5 micrometer. Well, that is something where we could have start thinking where maybe low-cost sensor would be good as a complementing instrument there. So if we don't measure particles smaller than 0.4, then we are many times underreporting the concentration, especially if we have a single particle counting. So it's not counting the small particles, calculating the mass out of it with underreported concentration. On the other hand, we have a problem with particles larger than 1 micrometer. They have already their own inertial life, and it's not easy with a little fan to get particles larger than 1 micrometer into the low-cost sensors, but they have a lot of mass. So if we lose few 1 micrometer particles, it is the same as we would lose few million nanoparticles. We have to consider that the efficiency of the intake of particles larger than 1 micron for low-cost sensors can be a problem. And then the ambient conditions. When we have a higher relative humidity, usually we'll have a hygroscopic growth of particles. Particle will be bigger. Bigger particles has a bigger optical signal, so we will have a higher reported PM2 point mass. It's not a surprise. we can correct for temperature and relative humidity, and some low-cost sensors start using this so-called Köhler theory to correct, at least to some extent, the possible particle growth due to the ambient conditions. So some low-cost sensors manufacturers do some certain corrections, but we don't know what. It's only done by factory software. So we are back to the question of the black box. Well, let's conclude what I was trying to share with you after some analysis, what is around us. If optical low-cost sensors, so optical sensors specifically, because there are others, are to be used for accurate particle exposure measurement or for compliance monitoring in the future, this is what Ajahn Pirapong mentioned at the beginning before I started, there is a must for further development of low-cost OPCs, and they will be done. But extended studies are still needed, and this is on us. Because due to the broad availability and really bargain prices for the low-cost sensors, there's also growing engagement of public and various interest groups. People will measure and say, well, today PM2.5 concentration is 500 microgram per cubic meter. I mean, my dear politician, you should do something. And the problem is on us. This public engagement must be scientifically confronted by us. We must be able to say, well, what you are measuring is based on our firm data, only a general information, and you may have an error of 200%. So we need to guide this public measurement of public data. So that would be conclusions of my talk, and I'll be very happy to discuss if you have some questions. But to be more positive at the end, I like to show this picture because I say if there were no atmospheric particles, maybe Claude Monet would have never painted these beautiful pictures of the sunset at the Parliament. Thank you for your kind attention.
Thank you very much, Wladyslaw, for a very, very interesting talk, and end up with the Monet's nice picture of scattered light through the atmospheric aerosol. Okay, and now it's time for question. Anyone has a question, please?
Can I have a question, please?
Yes.
Yes, please.
So thank you very much, Professor Wladyslaw. So it's very interesting topic and very hot topic now in Vietnam about a low cost sensor. And as you see that this morning, I also mentioned that in Vietnam we have a 63 province city. However, that we don't have enough automatic air quality monitoring station. That's why some private organization they install the low cost sensor to measure. But the question now is about the accuracy. So they think about the calibration like you, but you did very detailed, and it's a good job. So in Vietnam, they concern about the accuracy of the low cost sensor. Sometimes we have a lot of smoke and cloud, something like that, and they make the error until 30 to 50% error. So that's why the people they don't want to use that kind of data from low cost sensor. So recently the policy they think, and they will make the draft of policy to request the low cost sensor should be certificate, calibrated and certificate by famous organizations like US EPA, TUV Germany, Ministry of Environment Korea, and Ministry of Environment Japan. If they implement that measure, that policy. So almost the low-cost sensor in Vietnam will be, how can I say, will be stopped, cannot measure because they do not allow to publish that kind of data. So what do you think about that? About this situation, if they allow only four organizations to certificate only? Thank you.
Yes, well, you are addressing important issue because once you start, as I say, expensive calibration of cheap sensors, then they are not cheap anymore. Since I spent, fortunately, some time in Southeast Asia and visited some countries, I realized that people are very much tempted to use a very inexpensive sensor. And I think this is something which is valid and good. And I know it will not be a certification, but as I indicated, if I would use low-cost sensor, I would use definitely for ambient measurement low-cost sensors, which are measuring not single particles, but nephelometric measurement from many particles at the same time. They are less sensitive to quick changes in ambient particle situation. And then I think that having this great network which you have, most of the participants have no problem in obtaining one or two low-cost sensors. And I would just run parallel with your PM 0.1 and PM 2.5 and PM 10 measurements with more research-grade instruments on the sites where you are measuring, also low-cost sensors, where I would rather tend to use a low-cost sensor, which is, as you remember from my slide, maybe L0 or L1 level, where you are getting data and not too much software, and basically observe how this sensor behave and perform. And next to the data on mass concentration, on ECOC, etc., you can show the low-cost sensors, and then having ambient conditions, which are also measuring temperature and humidity, you can have your own correction scheme for low-cost sensors. As I said, this will not be certified, but then if some people would ask you, well, I'm measuring with this and this instrument, the low-cost sensor, and I have this concentration, then you can say, well, we are using these three types of low-cost sensors, and they agree with our measurement within plus minus 50%, but if you correct the data for temperature, they agree within plus minus 30%. And I think this is really a big achievement. So this is how I would proceed without making a very expensive trial to certify a very inexpensive instrument.
Thank you.
I hope it answers the questions partially.
Thank you.
Other questions? Now, in Thailand now, there's a group of the developer of the low-cost sensor system trying to push to have another supplementary platform of the low-cost sensor to the regulated platform by the pollution control department. But this is a supplement, and they are supported by the NRCT to do the field calibration with the TCD instrument, and under testing now in 3 stations. And preliminary result is as what you described. We have some error according to the temperature, relative humidity, and we need some correction. And then after that, the error may be about 20 to 30%, and could be acceptable for the use as a supplementary, not the replacement.
Yeah.
So
I agree fully.
This is a good direction for the government to do it.
Yes, I think so. When people realize that these instruments are providing data plus minus 30% or 40% after some corrections, And then also the public or interest groups which have access to this inexpensive instrument will realize that not everything they see on a display mirrors the real ambient situation. And this is very important, because otherwise you will have in any country millions of people who are measuring, and everybody has a different data. However, I must say that there are publications which are showing that if you have a distributed network of very, very many sensors, let's say 500, and 200 of that are measuring garbage, still from the 300 by statistical means, you can get a very good mapping of transport and average values of pollution. But only if you have very many. If you have one instrument, you will not see, or two or three, any trends. So I think the idea is, yes, low-cost sensors can be used, but they have to be used carefully. They have to be observed how they behave based on ambient conditions, and especially the relative humidity is a very big issue, particularly in Southeast Asia.
Okay, thank you very much. Any other questions?
Thank you very much for a very interesting talk. And I think one of the biggest problems with the local sensor is the aging. I mean, the changing in the performance while we are using it. I had some story in China. They already had some network with local sensors, but the biggest problem for them is the maintenance. Yeah, we should be sure always about the accuracy. Of course, accuracy is the most important, but how long? And when we use it, when we read the measure data, is it reliable? So that is the biggest problem. So that they use the network of local sensor for just detecting some event. Yeah, and so I'm not responsible for. So if we can find the location on the emission sources or some other people that we are not guilty for that. This kind of things they are using.
Yes, yes, this is very important issue which you're addressing as well, because with the low-cost sensors you have also similar problem like with the filter. You can overload filter and lose a lot of information. The low-cost sensors can be overloaded in two ways. Number one, if they're exposed to very high concentrations, they cannot handle very high concentrations. They will run in the situation where any further increase of signal is not measured. So they are saturated. This is one situation where people basically push the button and see sometimes too low concentrations because the sensor cannot measure more than a certain amount. The other situation is actually the long-term performance. And the solution is horrible, because basically we would be producing a lot of electronic garbage, because when you use a low-cost sensors, let's say in some ambient conditions for 1 year, and the sensor costs 1,000 baht, it is much cheaper to throw the sensor away and buy a new one instead of try to clean it. By the way, the sensor were never meant to be open and clean. And you know, particles is a dynamic system. So when you pull air with particles through the sensor, you have also nanoparticles around you, which you are pulling in the sensor. You don't count these particles because they are small. They are, let's say, 100 nanometers. You can catch these particles within the initial filter, and after very, very careful preparation and evaluation, you have the mass of these tiny particles, which is very difficult to measure. Now, these particles, when they get into the low-cost sensor, these particles are called sub-countable particles. Particles which are passing through the low-cost sensor, but they are not measured because the scattered light from the particles is too low. the detection system is too poor to measure. So you have any time in low-cost sensors, small particles, which you don't count, but you know this is an issue which Dr. Wada addressed, but they diffuse very well. So inside the low-cost sensor, they diffuse to all surfaces. They cover the surface of the detection part. They cover the surface of the light emitting diode or semiconductor laser. So you are changing basically the performance by the deposition of particles, right? And that's why with the time, the instrument deteriorates. So on one hand, it's a blessing because it's cheap and maybe it is useful. On the other hand, is a question, well, we will have probably soon as many low-cost sensors as we have face masks due to the pandemic, because we're using face masks and we're throwing that away, right? So it is a big problem. I agree. I don't know how to solve it.
Okay, before we end this talk, I have a couple of questions. First, I think that your point is very important about the maintenance. We don't just buy it and hope it can work forever. So proper maintenance is very important. The first question is that you said that we lose the count of the sub 0.4 micron particle, right? The loss of the sub 0.4 micron particle, but even we lose those particles, the count of the concentration from this low-cost sensor is still higher than the FRM or other methods. So I think the loss is not as important as other factor like the influence of the temperature or relative humidity, right? The second one is that since you said that the count of many particles together at the same time is not very sensitive to the characteristic of the particle, like the index of refraction. So the calibration at any places would be fine. No need to do it at different places, like in Chiang Mai or in Hat Yai, we can do it. We can expect the same calibration or not. Thank you.
Yes, well, both very interesting questions, and both would request usually more than a simple, quick answer, but I will try to make it quick. You are right when it comes to particles smaller than 0.4 or 0.3 micron. If there are many in a nephelometric instrument where we measure scattering from many particles, some of them will be counted because there are many. So they will deliver some signal which is measurable. And if you convert this data into mass concentration, then the error from those sub 0.4 micrometer particle is not usually very large when it comes to mass concentration. The other question was about the measurement, not from a single particle, but from a population of nephelometric measurement, from an ensemble of particles at the same time. I based my statement here on the fact that some time ago, we quite carefully looked at the performance, not of a low-cost sensors, but of nephelometric devices. And when we're using a polydispersed aerosol with changing refractive index of various materials, where our range of materials, we didn't use metallic particles. So I cannot say anything about metallic particles, but we're using and modeling performance when we were changing the refractive indices in the range of what you can expect in the atmosphere. Because you measure many particles at the same time, and they are not all of the same type, the influence of slight changes of refractive index do not impact the final mass concentration which you are getting from such an instrument. So we are looking at that time at the photometer which was built by originally by MIE, and then taken over. The company was taken over by Fisher, and this is based on our measurement and on our modeling. So when you have a polydispersed ambient particles, some of them will be absorbing, some of them will be not absorbing. But when you have a calibration curve in terms of mass concentration based on scattering from very many particles, a certain changes in refractive index will be, how should I say, will be smoothed out by the system. If you have a calibration for average atmospheric aerosols, which you may have, let's say, in Hachai, but you would move to Bangkok, where you may have more, let's say, absorbing particles in relation to other particles, could be that you are off with such an instrument. That's why I think it's a good exercise, and I don't see many publications so far where people would look at the low-cost sensors, trying to look at the response from the low-cost sensors, exposing this to particles, ambient particles, where we know the size. What I mean by that, if you have a low-cost sensors and a DMA or SMPS system, you can select some size fraction, or you can select some size fraction using impactor or some other size determining unit, and put these particles in the low-cost sensor, and then we would learn more about it. So I hope that this answers roughly your question.
Yeah, thank you so much. It helps a lot. Yeah, and I think the time is up. Would like to move to the next. Thank you very much, Dr. Szymanski, and hope you have a good time in Vienna, and looking forward to seeing you soon in Thailand. Thank you.
Anytime it is possible, with pleasure. Thank you.